Nadira Usal, and I'm going to start my presentation from the heading Theory of Equilibrium. When all the forces that act on an object are balanced, then the object is said to be in equilibrium. When a body moves on a smooth curve, then it takes the different positions. It will rest at points which are at positions of minimum and maximum of the curve. And if we slightly displace the body from the position of rest, then it will try to come back to the original position at rest, or it will displace from the position at rest and will try to go further away from the original position. The types of equilibrium. When the body is slightly displaced from its position of equilibrium, then equilibrium is said to be stable if the forces acting on the body bring it to the original position. The equilibrium is said to be unstable if the forces acting on the body bring it away from the original position. And the equilibrium is neutral if the forces acting on the body remain it always in the position of equilibrium. Conditions for the equilibrium. The conditions for stable equilibrium are if f dash theta is equal to 0 and f double dash theta is less than 0. It is also the condition for maxima of the work function W. The condition for unstable equilibrium are if f dash theta is equal to 0 and f double dash theta is greater than 0. It is also the condition for minima of work function W. The application of theory of equilibrium on strings. So here we can see from the figure, we'll consider P x y and theta x plus del x and y plus del y. These are the two neighboring points on the curve formed by the string. So here AP will be equal to S and AQ will be equal to S plus del S. So PQ will be equal to del S. Now we have from the figure T cos psi is equal to T dx upon ds, that will be equal to Fs. The resolved part of T plus del T along x-axis will be equal to y s plus del s, that will be equal to Fs plus del s f dash s plus del s square upon 2 factorial f double dash s and so on. So which will be equal to T dx by ds plus del s d by ds T dx by ds. So the component of T along x-axis is the sum of component of external forces along x-axis and the component of T plus del T along x-axis. That will be T dx by ds equal to m del s x plus T dx by ds plus del s dq by ds T dx by ds, which will be equal to m del s plus del s d by ds T dx by ds will be equal to 0. Now dividing by del s, we will get d by ds T dx by ds plus mx is equal to 0. In the similar way, along y-axis, we will get d by ds T dy by ds plus my will be equal to 0. These will be the equation 1 and 2, and from these equation, we will get the equation T d square s upon ds square plus dt by dx by ds plus mx is equal to 0, and similarly equation 2 from the equation 2. Now if we multiply these equation by dx by ds and dy by ds and we'll add these two equations, we'll get the equation T dx by ds d square x by ds square plus dy by ds d square y by ds square plus d by dt by ds dx by ds whole square plus dy by ds whole square plus mx dx by ds plus y dy by ds will be equal to 0. Now we'll get dx by ds whole square plus dy by ds whole square is equal to 1, which implies 2 dx ds d square x upon ds square plus 2 dy by ds d square y by ds square will be equal to 0. Now to plus dt by ds plus m x dx by ds plus y dy by ds will be equal to 0. So we'll get dt is equal to minus m x dx plus y dy. So t will be equal to, on integrating, c minus m integration x dx plus y dy. Now, points of central axis. So from the figure we can see that a line through a rigid body which is parallel to vector sum f of a system of forces acting on the body and which is located so that the system of forces is equivalent to the forces f applied everywhere along the line, plus a couple whose torque is equal to the component of the total torque T exerted by the system in the direction of f. This is points at central axis. Now, application of theory of equilibrium on virtual work. So in mechanics, virtual work arises in the application of principle of least action to the study of forces and movement of a mechanical system. An important benefit of the principle of virtual work is that only forces that do work as a system moves through a virtual displacement are needed to determine the mechanics of the system. So these were the applications of theory of equilibrium on virtual work, and now I'm going to end my presentation. Thank you for listening.